Hello. So I'm Taavi. I'm visiting PyOhio from Canada. I flew down from Toronto yesterday. I work at a company called Freshbooks. We do online invoicing. Freshbooks was very kind to send me down here to present and also to attend the conference. They're one of the conference sponsors as well. Just a bit of a survey, because there are two halves to this talk. Who's really here for the date time part? And who's really here for the log analysis part? All right, so that's a pretty even split. So I'll try to actually split it down the middle then. I've done the first talk before, the second talk, this will be the first time. It seems a lot longer than I intended, so I might rush through a few bits. I'm quite happy to hold an open space afterwards if anyone's really interested in digging into the log analysis parts. So let us start with date times. What you need to know about them. To start, time is complicated. I know a lot more about it than I did last year or before PyCon when I gave this presentation the first time. And I'll probably know more after this presentation, after the Q&A. There's a lot of learning that everyone can do from everyone else, especially on this topic. We'll go over what is an instant, look over different time standards, because it's important to understand why time is the way it is, to understand why is it so complicated. Looking over time zones, and then over the Python modules that you can use to interact with time, and then looking into interoperability. Not everything is Python. So an instant, according to Wikipedia, an infinitesimal moment in time. So an instant could be 10:30 a.m. Today in California it can be the same instant as 1:30 p.m. here. They have different representations, but they represent the same instant in the different time zones. But really, that's just one time standard in different time zones. There are different time standards, different ways of specifying how time passes. We have UT1, TAI, UTC, POSIX. UT1 is probably the equivalent of sort of the oldest time scale, but in a scientific way. It's time as defined as how far the Earth has rotated. So that noon is when the sun is directly overhead. And it varies with the tides and with weather and incoming comets. All those things affect how quickly the Earth rotates from day to day. It speeds up, it slows down. So the length of a second varies. But there are always the same number of seconds in a day. It's just they're all of variable length. And TAI is then International Atomic Time, which started in the late 50s and officially then, I think, in the late 60s. And it's the average of about 200 atomic clocks worldwide. In addition to being their average, they're all recalibrated to be as if they were at sea level, because how high up the atomic clock is actually adjusts how fast time travels. And so it's the average of the adjusted clocks to try to assume that they were on a perfect geoid. And TAI counts exactly 86,400 seconds of exactly the same length every single day, which means that it's drifting out of sync with reality. UTC, on the other hand, ticks exact SI seconds that are always the same length, and therefore a little bit shorter than UT1 seconds. But we want to keep it in sync. We want UTC to actually have noon as noon. And so whenever it looks like it's going to fall outside of 0.9 seconds from UT1, they insert a leap second. And we actually just recently had one. And there was quite the flurry on Twitter of people complaining of all the machines crashing. And it's funny because this isn't the first leap second we've had. There was another one, I think, 2.5 years ago. And then there was an 8-year span before that when there weren't any. So you'd think that people would have figured out that, yes, these things actually exist, but apparently not yet. Since 1972, UTC has been an integral offset from TAI, but that wasn't always the case. So there's this wonderful picture that I found on someone's website that shows UT, which is UT1, time according to the Earth's rotation angle, as compared to radio broadcasts of UTC. And you can see in around 1972, it started to stair-step, and that's when we get integer numbers of seconds. It's interesting to note that GPS is locked into 14 seconds ahead of TAI, but it's locked there. GPS signals will include the number of seconds offset that UTC should be from the GPS signal. Unfortunately, they only encoded it in 1 byte. So once we hit 128 leap seconds, you hope that you've upgraded the firmware to understand that it really should be 128 and not negative 127. Otherwise, you'll be 4 minutes late for everything. So then we get onto the kind of timestamps that most people who deal with computers talk about, which you call it a UNIX timestamp. Really, it's a POSIX timestamp, standardized by POSIX. And it is a count of SI seconds since 1970, except that there are no leap seconds. And so on a day that has a leap second, you get 2 seconds at the beginning of the day. And that can cause some very interesting clock skews with NTP. The NTP protocol actually defines extra information that says a leap second is coming, get ready for it, get ready for it, get ready for it. And when it actually happens, it doesn't say this, doesn't include the leap second as an extra field, it just, the time holds. But you were given warning, so you should be okay. Most systems just ignore the warning and suddenly are 1 second out and freak out, and usually takes about 20 minutes for NTP to skew back to normal. POSIX timestamps do take leap years into account, according to the Gregorian formula, where you have 365 days in a year, unless it's divisible by 4, but not if it's divisible by 100. But yes, it's a leap year again if it's divisible by 400, and that's why 2100 will not be a leap year, but the year 2000 was. I believe there's another term for every 4,000 years that makes it correct over even longer spans of time, which we haven't hit yet, but we will eventually. And the interesting thing is that the whole idea of leap years didn't come up until October 1582, when the Pope Gregory, hence the Gregorian calendar, said, well, this is how we should be doing things, because people were starting to worry about crop failure. You're supposed to plant your plants on a certain day of the year. And if that day of the year starts to drift away from the optimal planting time, you start having serious problems. So we have 2 kinds of leaps. We have leap seconds, which keep noon at noon, and we have leap days, which keep the equinox and solstices at the appropriate times of year, so that summer remains summer. So next we get into time zones. And it used to be that every town had their own clock that was calibrated to local noon. It would be basically like a UT1, where when the sun's directly overhead, it's noon. But everyone would be different. They'd be 5 minutes off, 7.5 minutes off the next town. You had no idea. So it's no wonder the trains never ran on time. Nobody knew what time it was. And the first time zone was in Great Britain to help keep the trains running properly. So we get this other nice map showing all the different time zones in the world, some of which do daylight savings. If you look all the way over here at Ontario and Ohio, you get -5 or -4 depending on daylight savings. But other places like China just stick to an offset to UTC, +8 year-round. It's important to note that GMT is not UTC. GMT can mean a couple of different things. GMT historically was the mean solar time at the Greenwich Observatory, which means it's very close to what UT1 is. And if you don't care about sub-second precision, that's not a big deal at all. But it can be very confusing if you're trying to schedule a meeting with someone. And if you say, you know, yes, you're in GMT and I want to schedule this meeting for 1 p.m. today, and we want to have this meeting again in 6 months. Well, which side of DST are you on either side? If they're in England, they're not going to be on GMT the entire year. They're going to switch to BST for part of the year, just like we go from EST to EDT and back. So it's important to know if you mean UTC, or do you mean GMT and therefore you want to switch to BST when it becomes appropriate. UTC never has daylight savings. And in a historical context, GMT was used by astronomers, and astronomers do their observations at night. And they like it when all their observations fall on the same calendar day. So they defined midnight as when the sun was directly overhead. So you're never sure if you're 12 hours out if you're looking at historical GMT readings. So really, in the words of Armronacher, just use UTC for everything in your computer programs. Store it that way, measure it that way, and don't use offset-aware date times. And I'll get into what I mean by that in terms of Python. If you're taking user input in local time, make sure that you know what time zone it's in. If it's ambiguous, make sure you ask the user, which one did you mean? Did you mean 1:30 in the morning or 1:30 in the morning? It can matter. Or if the user says 2:30, you can say, there is no 2:30. Make sure that you ask that, otherwise you don't know what data you just recorded. And obviously rebase for formatting, give the person time in local time. You might want to tell them whether it's daylight savings or not. Maybe, maybe not. In the past, you know what it was. Going forward, well, you never quite know when daylight savings is actually going to kick in. So let's get into the Python. There are 3 built-in modules that really help with date times, and then there's 1 external module that I highly recommend you use if you need to use any kinds of time zones, which, believe it or not, includes UTC, because the standard library does not even ship with the UTC time zone, which is kind of strange. The time module is a C module built into Python. It's essentially your interface to the libc functions for dealing with time. It's like the thread module and calling os.fork. It's very low level. And time zones are supported, but only by setting an environment variable, which means you get 1 time zone for your entire program at once. So it's not very flexible. You can't really convert between 2 different time zones. And you can specify daylight savings, but it's a flag on the struct time. And so your environment variable says what set of time zones you're in, and you can say, am I in DST or not? But it's explicit instead of being implicit in what time of the year it is. So the DST flag helps to disambiguate that 1:30 once a year. And you can use time.time to get the current POSIX timestamp for your system. And you can call time GM time to get a struct time representing UTC, either for a given POSIX timestamp or for right now. And the calendar module is completely unrelated to date times. The calendar module is for making nice little printed calendars that shows the days of the week printed out week-wise. Except that it also has this nice little utility function that will take a time tuple, a struct time basically, and convert it into a POSIX timestamp. There was a bug open to finally maybe move it over into the time module, but it ended up being rejected. Things about Python versions and C versions and not being exactly compatible, and people were worried about it, and so it didn't move. So just know that it's in the calendar module. Date times are really the rich interface that you want to use. It's the one like threading and subprocess where it provides a nice Pythonic wrapper around all these other behaviors. There are 2 varieties of date time. There's the naive type, which doesn't know what time zone is associated with it. It's just a date and a time. And then there's the aware time, which knows what time zone it exists in, and the exact offset. The 2 of them don't mix. You can't add them, subtract them, do anything like that. You can do that only with completely naive ones that will ignore daylight savings, or ones that understand all that. And unfortunately, there are still a lot of sharp edges with these. Dealing with time zones with date times, there are basically some things you should do and some things you should not do. And that's probably the simplest way to work with them unless you really need to delve in. Do use the PyTZ library. It ships with its own copy of the Olson time zone database, so you don't have to rely on the system installed version, which can be really helpful on Windows, which doesn't actually ship with anything approaching the Olson time zone database. It comes with all the necessary helper functions to make aware date times properly. And you do have to update it regularly. So if you lock egg versions in your packages, which you should, you do have to remember to constantly update that, even if the package itself, if your software hasn't been updated, you might want it to have the newest definitions. Things like DST changes a few years ago, when daylight savings happened in the US and Canada, got moved, and you need an updated version of PyTZ to get that kind of thing. And other countries throughout the world change their time zone information constantly. So do make UTC aware date times the really easy way. You can just pass the UTC time zone into the datetime constructor and everything's happy. Because UTC has no offsets and no daylight savings, you have nothing to worry about. You can just plop it in. That makes a nice aware one if you need it. Do use the localize method on PyTZ time zones in order to get an appropriate localized time. So you can take a date time, like November 6th at 5:30 in the morning, 2011, and say, that's what the wall clock says in Helsinki. Can you give me an aware date time so that I can do other kinds of date math? And that will do it properly. It says, oh yeah, at 5:30 in the morning, that was EET +2. Cool. And you should also tell localize to not guess if you're not sure if it will work or not. And if you pass isDST none, it'll throw an ambiguous time error saying, which 1:30 did you mean? I don't know. And in that case, you should ask the user, which one did you mean, instead of just trying to guess. And it's really easy to find out what date it is in a given time zone. You can say datetime.now given a time zone, and it'll give you a perfectly happy aware date time for that location. And you can just ask for its date and get back the fact that it was March 5th when I ran that. So that's really nice. Things you shouldn't do. Don't try to make non-UTC aware date times by just passing TZ info in. June 1st is supposed to be in the summer. It's daylight savings time, but if you just pass it in, you'll get EST, -5, instead of -4 like we are right now. The datetime constructor doesn't ask enough of the time zone when it gets constructed. So you have to use the time zone's localized method to get that to work properly. Also, don't make, oh yeah, and that's just, hello? What happens when you use the constructor this way is that it will use the very first definition for that time zone. And the first definition we have for Europe Helsinki is from around the 1910s. And they were 1 hour and 40 minutes off of GMT at that point. And you never want that, especially not in 2011. So don't do that. Replace has exactly the same problem. There's an as time zone method that you can use that works properly. In trying to actually show how you convert from all these different formats, I ended up with this, which looks nice, but is actually really hard to read. So I turned it into a web page instead. And so you can mouse over and say, okay, I need to convert from a naive UTC date time into a struct time. How do I do that? Okay, I just called UTC time tuple. Cool. So that one is available on my website at the URL you see at the bottom. So if you see the video, you can just head over to there. So interoperability. The world is not all Python. We have databases we need to interact with, and sometimes even web clients. MySQL has dates, pure dates, easy. Datetime, which is like a Python naive datetime, no time zone information, and a timestamp, which gets stored as a POSIX timestamp internally and gets converted on input and output based on your connection time zone. So that's like having an environment variable. It's a very global thing. What you probably want to do with MySQL is to set everything to UTC just in case, and then just use naive date times and understand that all your naive date times are in UTC. And if you need to store time zone information, store that in a separate column. Store the full time zone name from the Olsen database, and then you're fine. There is a convert TZ, but I'm pretty sure it will bite you in terms of DST, unless you store everything very concretely. You know, oh, this was in EDT, this was in EST, instead of just, oh, it was in one of them, because then you still get ambiguous errors at 130. Postgres, I haven't used much. There were some good suggestions at the PyCon talk, which unfortunately I've since forgotten, about how to use Postgres with time zones. But it has dates, it has times, including time with time zone, which is kind of a ridiculous concept without a date attached. And then a timestamp, which is stored internally as seconds since January 1st, 2000. But essentially that's just an offset from standard POSIX timestamps. And then again, that gets translated on I/O based on the connection time zone. So probably set the connection time zone to UTC and be happy. There is the @timezone operator if you need to translate in the database, but the database is usually the wrong place to do those translations. SQLite is even simpler than those. You can store dates in a text column, because that's one of, I think, 5 types that SQLite actually supports. And you can just use your 8601 string, or you can store it as a real number, which is a Julian day number, which is not the, oh yeah, according to the proleptic Gregorian calendar, that's taking the Gregorian calendar, which only started in the 1500s, and pretending that it goes back in time. I'm not entirely sure why you'd want to do that, because none of the history books know anything about Gregorian times. Or you can store it as an integer, standard POSIX timestamp, and there are functions in SQLite to deal with these and to do some amounts of translation. But really all it supports is whatever the local time happens to be, and UTC. It's about all you get out of it. JavaScript is kind of the same way as SQLite. There is a nice data object that will have the local time zone and the current DST setting, and you can get UTC values out of that, which is nice. You can know exactly when now is. And you can interact with POSIX timestamps, understanding that JavaScript always thinks in terms of milliseconds. All the timing values are all in milliseconds, so you need to multiply by 1,000 or divide by 1,000 to convert between JavaScript timestamps and POSIX timestamps. And don't try to do anything in a different time zone or across DST boundaries. If you ask JavaScript, what's now 6 months from now, it will assume the current DST value, and you'll be off by an hour. So I read a whole bunch of things. I know I read even more. That's a large list of them. That is that. I had a couple more slides, but we're going to move on to the next presentation now. Are there any quick questions on that before we move over?
What was the URL?
The URL for which?
For your conversion?
Oh, yes, that. TaaviBurns.ca, what you need to know about datetimes, datetime transforms. Yes, it's really long. I will put one up. I will do that. I will put a link on TaaviBurns.ca to that. Mm-hmm. Okay, so there's a. Okay, someone was just saying for the recording, there's a Postgres temporal extension, and under the covers it was storing everything as date times with time zone, and that was causing problems. You need to make sure to convert everything to UTC when you pull it out, otherwise you get weird errors. Yeah?
I had a question too. I've been doing a little bit with Datetimes and Timezones. I noticed in your outline you mentioned date.
Python date util.
Yeah.
Yes.
And you use that for anything related to time zones? You mostly use it for offsets, or what place do you think that has in your policy?
So Python date util is like PyTZ mostly. I think most people use it as an interface to the Olsen time zone database. Python date util uses the system database, which is nice. Sysadmins can just upgrade the system library and you don't have to upgrade your Python package. But Python date util doesn't have a localized method. It gets daylight savings time wrong consistently. I filed a couple of bugs about it back when I was doing this presentation for PyCon. So it doesn't do things correctly. And so I'm like, I don't really need this right now. So I do need to move on to the next presentation. If there are any other questions about this one, I'm happy to entertain them at the end. So let us move on to log analysis. So what kind of log analysis? Doing things like graphing requests per second for a particular kind of request and showing various before and after characteristics, trying to show how did performance change as a result of a code change. So we have some tools to deal with doing this, the actual log files that we're going to be analyzing, and then how we can do the analysis. I'm going to go through the slides really quickly. I have some interactive code examples that we can go through. I have a feeling people probably want to look at the code more than the slides, so I'll go through the slides quickly. So we have IPython, which if you haven't used it is a really neat interactive Python interpreter. It has a bunch of tab completion features in that. You can use it as a console REPL. It has this nice shell. It has a bunch of parallel computing tools, but also the IPython notebook. And the IPython notebook is really awesome. It includes a JSON-based notebook format so that you can write interactive bits of code and rich text and even math, and save it, bring it up later, distribute it to friends, all of that, and also a web-based interface for working with these notebooks. So you get an interface like this, where in the web browser you have windows and you can type in bits of Python code and see how they evaluate, and go back and reevaluate things, save the whole thing, restart the kernel, all of that. It does need 0MQ, which is relatively easy to install using Homebrew. If, like me, you're still running Snow Leopard, but you have Xcode 4, you have some fun and games because it tries to compile PPC extensions that it can't. And then we have matplotlib. If you install matplotlib, then you have a wonderful extension called pylab, which is a set of Python functions that look and behave a lot like being at a MATLAB prompt. So you can just say, plot me a thing. And there's beautiful integration with the IPython notebook so that you can get inline graphs in the web browser as you're typing stuff, which is a really fantastic exploratory tool. So those are the basic tools. Next up is parsing log files. it would be really nice if everyone just logged JSON or some other machine-readable format for their logs. And I know some people already do this, and I have a feeling that most people still aren't. It would be nice if people needed a human-readable version of the log file. You could write one program that would read and write out readable stuff. And then all the programs that you write could just read new statistics as you started to write them. But usually we end up with log files that look like this, which leads us to write code like this to try to rip out the important bits. And even worse is that the time format that our syslog was writing isn't something that you can directly interpret with Python because of the time zone information that it was storing, -4 or -5. So here's the horrible thing, as you know from the datetime presentation, where you have to take a struct time with the year and all these things, and then you have to figure out the time zone offset. If the time zone offset had a plus, it means that we're ahead of UTC, and if it's a minus, it means we're behind. So if it's a plus, you have to do a subtraction. If it's a minus, you have to do an addition. So tzdir is used to adjust the sense of the offset, and then smack that on using timegm. And now we have a nice POSIX timestamp for each of these records, so that even across DST boundaries, we just have this nice monotonically increasing thing, so that when we do graphs, they look sane. Oh, wrong way. So once we've used the regular expression, you notice I used a lot of named capture groups. Named capture groups are really awesome in a regular expression. It means you can capture more things or fewer things, and as long as you only look at the bits that you extracted, you can basically just get a dictionary out of all of the things captured. And what's really nice if you want to store it is to use a named tuple. Named tuples are small, they are fast, they are memory efficient. And it also means that when you need to transfer files, the gigabytes of logs on the server would take a long time to download, and sometimes there are issues of privacy. What's in those log files? Do you really want them on your local workstation? Probably not. And you want to be able to write them out. And you could do something like JSON or message pack, but then you're recording the keys for every single log entry, and you know what the keys are. It's a nice tabular format. So really, you can just use CSV. CSV needs things in a consistent order. Named tuples are a kind of nice way to take a dictionary and get things into a sane tuple order. So let's do a little bit of log munging. So here are those same example log lines, just listed out as Python strings. And there's the ugly regular expression for what I call the process accounting. And that is the things that we get logged on every log line. The date stamp at the beginning, which host it was on, and things like a request ID, which we generate a unique one for each HTTP request to our internal web server. And how long did the request take, and how much user time, how much system time, how much memory was consumed, all of that. And then for our internal web application, we have different resource endpoints, a RESTful-like interface. And so the resource RE tries to extract that bit of information from the log lines that contain it. So we know which account the person was accessing, which user ID were they, which method were they accessing, how many rows were returned from the database of the primary resource we were trying to extract. And then one that says full request. We do log one last log line for every request that just says, here's the full time that took, including serialization for our response, all of the time. So that's how we can detect that. And so we need to amalgamate the log entries. And this is a little bit ugly, but not too bad. We have a dictionary of in-flight requests, keyed by request ID. We use a default dict so that we can just update a thing in place. I don't have to worry, does the key exist already? I can just say, update the thing in place and be done with it. So we get the process accounting, we get the request ID from that. If it was a resource request, then we update the in-flight request with the group dict that we extracted from the resource. And then when we finally get a full request, we say, okay, this is the full elapsed time that we actually want to record. If the request ID wasn't in flight, then we got a full request, but we didn't see anything else. Maybe that was from yesterday. Maybe we just don't care. But if we do have a request, then update the request with the full process accounting, and then we yield it. We have a nice generator here, and then delete the in-flight so that the cache doesn't grow indefinitely. We have our add POSIX timestamp, and now we have a little bit of a schema. There are only some of these fields that I actually care about, and they have different types. I know that the timestamp is always an integer, that this other thing is always a string. It's not particularly interesting here, but it'll be interesting when we start analyzing. And so there's also this apply schema method, which will return a dictionary that has the field and each of the field values coerced into the specified type. And if we apply schema to the POSIX timestamp added version of a line for each of the amalgamated log entries, then we get a nice little dictionary. And this was generated from those first 2 log lines. So we can see it was this account. We can see which method. It was a search method. We see the timestamp, the query time, all of that nice information. And then we can create a named tuple. So from the schema, we take all of those names, and now we have a named tuple that has this consistent ordering of names. And Python has a nice little CSV module. You can create readers and writers, and you say, write this tuple, and it'll just write it out and do all the escaping and all the commas for you. And so you can say, for row in the amalgamated log entries, take the row and add the POSIX timestamp, apply the schema, double splat it in to get the keyword arguments into the record, and write that row after we've written the record's header fields, and we get a CSV file. And you can do that for an entire log file, and you get a nice CSV, which is fast to write and actually relatively fast to read as well. So, on to analysis. Aggregations. And really, we want to know things like, what's the median response time? What's the number of requests per second? And those are sort of the end statistics. We want to do some data munging before that. And we can do a lot of the data munging just with list comprehensions. We can say, we want it only for this time period, or only for this kind of request. And list comprehensions are a beautiful way to do that. Most people don't have big data. You keep hearing about big data and terabytes of data. Most people don't have that. Even if you've got gigabytes of log files, it's only gigabytes. I have 8 gigs of RAM in this laptop. It was cheap. Just doing things in pure Python is a really easy to understand way to process your log files when they're just not that big. And so really what we want to do is take all of these items and group them into little temporal buckets per minute or per 5 minutes, things like that, and then do some aggregation. We want to know the number of them in that time span, or the median of some value in there. And we can do that. Nice little picture I took on the airplane. All the events along the top, and then this mapping, grouping them, and then taking each group and reducing it, doing the aggregations into values, and we can get a little graph out of it. So the framework for doing MapReduce is like this. That's all it takes. You have your input data, and you have a mapping function that will tell you how to group things, and a reduce function that will take each of the groups and produce the aggregate value. And the itertools has a wonderful little function called group by. You give it a key function, and it'll give you each input, and you return a value. And group by will then return that value as k, and a list of all the items that evaluated to that as v, assuming that data is already sorted based on that key. And we're going to assume that we're going to group by time, and that the log files are actually dumped temporally. That might be a bad assumption, but it's worked so far. And then we append the keys and append the reduced value, and then we can just return a list of keys and values. And that's the kind of thing that you can just plot using matplotlib. The mapping phase to find out by minute is really simple. You just take the POSIX timestamp and integer divide by 60. Basically just a floor operation per minute. Reduce, if you want something like a percentile, gets a little bit trickier. There's a nice percentile written in pure Python available on ActiveState. It does correct percentiles for when you ask for the 50th percentile and there are only 2 items. It'll take the average of the 2. It'll do a weighted thing if you've got not quite the right number. If you have asking for the 75th percentile and you have some very strange number of items. It does all of that properly. And so we need a function that will just accept a list of things and return the aggregate. And so we have percentile of, and you say percentile of which field of this list of named tuples. And so it'll do a get adder to extract just the value we're interested in, sort it, pass it in as a list to percentile with the given percentile value. And we'll see an example of that. So you put it all together and you say plot the data for some list of records, where those records are these named tuples, by minute, because I want a per minute graph, and the 50th percentile, the median of the elapsed field. And it's really easy to just sort of slice and dice this. You can do your list comprehensions to adjust what the list of records actually contains. You can adjust by minute to do offsets or other stranger aggregations, and you percentile of. You can ask for any of the percentiles. You can drop in something very close to just len. Group by returns an iterator, so you need to convert it to a list before you can get that, or pass in some function that will simply count the number of items in an iterator. But it's all very simple, plain Python. So the next demo, I'm going to use some slightly sanitized subset of real server day that we get at work. Releases tend to go out on Tuesday mornings about 9 a.m. And we want to compare, if we're going to compare before and after a release, the same time of day, because we have cyclic loads. And there were some interesting changes I released on the 8th and on the 15th. So I have some data from the 7th, the 8th, the 14th, and the 15th. So we have before and after of these two interesting releases. So let's go look at some requests per second, percentile response times, and average database query time. Here's a little timing context manager so that you can see how long each of these phases takes. I've reproduced the schema here, which is kind of unfortunate. It kind of sucks that CSV doesn't store that kind of information. But it's not too bad to reproduce it here. Normally you'd put it off in its own module so that the log munger and the log analysis are actually using the same code. I played a little trick here to get the schema names and the schema types. You can use zip and splat it in, and that will take, whatever it is, 15 different tuples and give you two lists that has all of the first items and all of the second items. And then this is a really ugly hack just to make it a little bit faster. All it does is take a tuple and coerce it to the types there. So just ignore the evil. We have our named tuple again, just as simple as before. And then we go and start reading the CSV files. And the interesting thing here is disabling the GC. The garbage collector in Python collects cyclic garbage. It's not the ref counting part. And we know that we're going to be reading several million records, and each record will require creating a tuple and creating other bits of data. And we know we're not going to make any cycles. There's nothing to collect. And turning off the garbage collector makes it a lot faster, like 62% faster. And it also makes them take about 34 seconds each. Whereas without that, they take longer and longer because there are more and more items to try to collect every time, even though there's nothing to collect. So we can get a reader for the CSV file, read the header line. We make sure that the records fields match the header, just to make sure that someone didn't change the CSV format on us while we weren't looking, probably us. And then just force the schema on each line from the reader and make one of these name tuples. And now we have a bunch of lists of these things. In order to do filtering on these, we need the POSIX timestamps. Here we have Toronto time zone. We're going to call localize, given the datetime arguments. And we're going to ask it to explode if we ask for something ambiguous. And return the POSIX timestamp. Just a nice little helper. So yeah, pre-release would be May 7th. That's a Monday, the day before the release. So this, we can see what things look like before. We get the start, POSIX for Toronto at May 7th at 9 a.m. and the end, May 7th at 11 a.m. And we just do a nice little list comprehension, item for item. We're not copying the items, we're just copying references to them. And they're all tuples. So the list comprehension takes almost no time to filter out 200,000 records from, I think, about 1.8 million records. It takes a second. That's not bad. We can see the kind of data that we get out. So we have plot data for, just like in the presentation, by minute, the actual Python implementation of percentile, and the percentile of. And now we get into the PyLab part. We say we want a couple of plots. So we use subplot to say I want a top plot and a bottom plot. Set the labels. And then we can just plot the pre-release by minute. Remember I said it gets an iterator from group by, so we have to coerce to a list before we can call len on it. But it is as simple as that to get requests per second, or requests per minute. Actually, we didn't divide by 60. And then we can do other things like get the 10th percentile elapsed and the 90th percentile elapsed and just ask for those plot them together, and we get these nice little graphs. We can even ask more complicated questions like the average query time. So we no longer care how many requests came in or how many queries, but we want to know the average query time. We don't record the time for all queries, so we can't do percentiles, but we can do aggregations. We know the sum, we know the count. You can sum all of those and still do division, and it works. So the reduction that we do is we get the list of entries. We have to get a list because it's an iterator and we need to use it twice. We get all of the query times and sum them. We get all of the number of queries and we sum those. If there are no queries, we can do this nice little trick and return nan, because dividing by nan doesn't throw an exception. But it will return nan, so we know it's still not a number. And then just return total time divided by the number of queries. And then we can plot that, and we get a plot of average query time. And you can see it looks like someone was running some expensive queries there. We don't have much longer to go. So for the before versus after thing, we have some DTOs in our code that are basically a schema and a way of translating from JSON into our internal, or into SQL Alchemy models, and keeping track of which fields were actually passed in versus which ones were implicitly not, or which ones were set to none, and things like that. And they were constructed every single time they were instantiated, and you would construct a whole bunch of metadata about it every time, which is very simple to write and makes for nice declarative style, but instantiation isn't so good. Mike Pernat gave a talk at PyCon a year and a half ago, a exhibition of atrocity, which gave me the horrible idea to use metaclasses to make these DTOs go a lot faster. The instantiation is constant, so we should just do it at class time and not at object instantiation time. So fast requests stay fast because they didn't actually create very many of these DTO objects, but large requests for thousands of invoices, since we run an invoicing service, invoices are really expensive. They have lines, they have money amounts all over the place. And it showed that 99th percentile of all requests got a bit faster, but wouldn't it be nice to show that no, really it was this code change that caused these particular requests to go faster? So we have a hypothesis that the list requests for invoices that asked for the most data will see the highest speed up. And so we can go back here and see amount of data returned versus response time. So we're going to filter now on release day, on May 8th from 9 a.m. to 11 a.m. It's the same filter we did before. Takes about the same amount of time. We only care about invoice search. So we're looking for the data silo that's invoices, and we're looking for the search method, which is how you do listing. A list is a search with no search query parameters. It's just all of them. So we restrict ourselves to that. We have a helper function to get the rows, a helper function to get elapsed, because we're going to call these a couple of times. And all we have to do then is to plot a scatter plot of the number of rows in the pre-release versus the elapsed time in the pre-release as red pluses, and post-release as green pluses. And sure enough, after a very short period of time, we have a nice little scatter plot that shows that the red line shows that as we ask for more and more rows, it takes more and more time to respond. And you can see there's another line for after, and the slope is such that we can return more rows given the same amount of time. So yeah, it looks like we actually have this very nice linear speed up, exactly the speed up that we expected. We can show that a very similar data structure, estimates, if we go and look only for the estimate resources in that same time span, I didn't apply metaclassing to estimates in that release. And if we plot those, we see that they more or less line up. You just get parallel lines. We get the same data for 2 days in a row. So that confirms that we did actually see a change that was restricted to invoices, and it wasn't some general change to the entire infrastructure. And of course, after seeing that, I was like, woohoo, I have to finish this work. Let's keep metaclassing all the DTOs. And so if we look on May 14th and 15th, we can do our filtering for the time. We can then do our filtering for just estimates and plot that. And we see that when we release that speed up, we see the same kind of change in timing behavior based on the number of estimates returned. So I think that's basically all the time we have. That's 45 minutes. So I think there's a 5-minute time for Q&A. I have a whole other section to go through, but we should probably do the Q&A first. And like I said, I'm quite happy to do an open space sometime if people are really interested. Come up after the talk, and we'll organize a time to look into other stuff. So, any questions? So I'm going to have to fast forward through the other slides to get to the end bit. Impress.js. HTML5. It's just running in Chrome. It's all CSS, HTML, and a little bit of JavaScript. The patterns of slides is actually just code. You can specify exactly where you want things as well, but it was easier to just define a JavaScript function that would do the layout.
What was the idea for that active state recipe?
The idea for it?
The ID.
Oh, the ID. Let's get back to that. Oh, wait, I have that. I know where I can get it. It's in here. 511478. Yeah, as someone said. If you are using NumPy for anything, if you already have it installed, NumPy has a percentile function that probably performs better. Though on sorted data, it's, yeah, if the data is already sorted, it doesn't matter. The NumPy one probably doesn't require you to pre-sort the data. It'll probably do that under the covers for you. So. Yes? So that was the last part of the presentation that I had to cut off. I managed to re-implement a whole bunch of these things. So we're using the pandas parser's read CSV to read the data. It takes a bit longer to read the data, but once we have 1.8 million records, we can go through and do our comparisons using datetimes and use resampling to do the aggregations. And so you can get exactly the same plots. And these plots actually include UTC timestamps along the bottom because we're using the plot method on the pandas data frame. So we actually get UTC timestamps. There's a lot nicer than the other one. We just got number of data points as an index, basically. Or POSIX timestamp is a timestamp, which is not useful to humans. It's not very descriptive. And yeah, managed to get most of it working. Average query time wasn't quite agreeing. I wasn't quite sure why. That actually looks very similar, though. There's that same spike. Huh. And the average amount of data returned, we can get all of that. And it is actually less code once you get it working. You can see there's a lot less code for each of these graphs. But you do have to understand NumPy ND arrays to understand how pandas data frames work. So it requires more learning, but it's definitely a tool that exists and is getting better. Yeah. Yes, so at work, I'm using Graphite to visualize things. We have Munin as well. The sysadmins have that. It provides 5-minute resolution. I wanted something that was closer to minute by minute and could record many more interesting statistics. So a little over a year now, I wrote some very small scripts, which, again, munge through the log files and just look for the response times based on the host, based on which pool of worker it was, and produce the summary statistics. Just to standard out, and you can pipe it into Netcat, into Graphite. You can take logs from a month ago and backfill them if you suddenly decide you need a new statistic. So yeah, I really like using Graphite for that kind of thing. And it's kind of like doing this interactive stuff with IPython Notebook, where with Graphite you don't have to know the statistic you wanted to know. You can just throw a bunch of data at it, and after the fact you can compute things, you can lag things all in Graphite. So it's a really good tool for doing that as well. Any other questions? Cool. Well, I have t-shirts if anyone wants them. Here. And there are different sizes, so if you didn't get the size you want, just go find someone wearing a nice FreshBooks t-shirt. You want one? Anyone else? And one left. Uh-oh. So, one. And then there's one more hand, I thought. Oh, all right. Come on up and get it. I don't think I can throw that far. Thanks.